The first thing I thought I'd do is put in a plug for two things. One is my own cryonics website. That's www.merkle.com/cryo. The other site that I would really recommend to you is the Alcor website, www.alcor.org. It's really worthwhile. I think there was a large impetus given a few years ago to improvements in the website when we had all of the legislative action going on and we wanted to have the best information possible up on the website. And since then, it's just been getting better. So I just thought I'd put in that plug. Now what I'd like to talk about briefly is nanotechnology. Nanotechnology will give us complete mastery of this new and amazing capability. It will let us manufacture products that are of remarkable precision. We'll get almost every atom in the right place. And we should be able to achieve manufacturing costs that are not a lot greater than the cost of raw materials and energy. To give you a brief idea of what this means, it's sort of like the economics of manufacturing are going to shift over to be largely like the economics of software. So we're going to see a fundamental shift in our manufacturing paradigm, a fundamental change in how we go about doing business in terms of manufacturing. And this has a big impact on all aspects of our physical world, and it's going to have a very big impact on medicine. So nanomedicine is going to be a complete change. So one of the key ideas that I'd like to sort of bring to the fore is that at our size, we think nothing of holding parts and positioning them and assembling them. At the molecular scale, we don't have that yet. We're just beginning to be able to hold and position molecular tools, and we've seen some remarkable advances in that capability. So bringing that ability to hold and position molecular tools down to the molecular level is going to have a huge and very favorable impact on technology in general and on medical technology and cryonics in particular. Okay, so that's a really brief introduction to nanotechnology. What's the impact going to be? We're going to have very powerful computers. We will have computers the size of a sugar cube that have more computational power than all the computers in the world today. And I think I have to start being a bit cautious about that statement. I've been making that for many years, and I think time is catching up. I might have to bump it into a few sugar cubes at this point, because all the computers in the world today are beginning to have a fair amount of computational power. We'll have more than 10 to the 21st bits in the same volume. 10 to the 21st bits is approximately, well, you know what a CD is. It's about yay big. It has half a gigabyte of memory on it. Now imagine a football stadium filled up with CDs, crammed to the top. That is about 10 to the 21st bits. And we're going to be able to pack that into a sugar cube. We're going to have really amazing memory technology. And we'll be able to put almost 1 billion Pentiums in parallel. Again, this dates the talk. I'm not talking about Pentium 4s. I'm talking about old-fashioned Pentiums. We will have so much computational power that we will be able to run Windows 2015. Miracles, miracles, absolute. And it will be zippy fast. Completely astonishing. So let me then go into the scale of the kind of things we're talking about. In a sugar cube, you can pack huge amounts of computational power and memory. But if you're talking about medical applications, you might want something that's fairly small, something that would be able to fit through your circulatory system, for example. And in fact, when you look at it, you can shrink things down to the scale of, say, 100 nanometers on a side. And a nanometer, again, is a billionth of a meter. It's really, really small. It's only a little bigger than an atom. So a cube 100 nanometers on a side is pretty small, and we'll be able to fit a small CPU, probably an 8-bit processor, into that kind of volume. And we'll also be able to have robotic arms, positional devices that can reach out and position and hold things in at that size frame. And we'll have a whole range of other capabilities, all at that size. This is very small. It's much smaller than the subcellular organelles. And if you take an ordinary cell, quote unquote, is perhaps 20 microns in size. So we're looking at a huge difference in size. Abandon the idea that cells are these very, very teeny things. From the point of view of nanotechnology, from the point of view of molecular machines, cells are gigantic. They're these huge empty spaces, and you can pack literally hundreds of thousands of molecular machines into a single typical cell. This is going to lead to a fundamental change in medicine, a fundamental revolution in our medical capabilities. Right now, the key issue in medicine is to keep the tissue functioning. If tissue is not functioning, it cannot repair itself. We have no ability to repair tissue which is damaged beyond its own self-repair capability. We can provide support to the cells, but basically the cells are repairing themselves. As a consequence, cellular function must be preserved, because if cellular function is lost, the cell is on a downward spiral that we today are helpless to stop. In the future, with cell repair systems, we will be able to repair passive structures. So structures that are beyond our present medical capability, structures that are no longer functioning, but are largely intact, will be repairable by using molecular machines that are small, precise, and will be able to deal with the kinds of damage at the molecular and cellular levels that we see in those tissues. I cannot overemphasize the importance of this distinction. If you lose function, that happens relatively easily. Losing structure is difficult, and in fact, there's every reason to believe that structural preservation, the kind of structural preservation we get today, is going to provide enough structural preservation so that future repair technologies can, in fact, reverse the damage. Which brings us to cryonics. Cryonics, as you all know, is the idea of cooling tissue using the best currently available technology down to the temperature of liquid nitrogen, holding tissue at the temperature of liquid nitrogen, and then when we develop this future technology of warming the tissue back up, if you take a purely scientific view of what is cryonics and how do you tell whether it works, the first thing you'll do is you'll say, well, let's conduct clinical trials. Clinical trials are very simple in medicine. If someone wants to know whether a procedure or treatment is helpful, then the answer is you try it out and see if it works. Well, this is what we would like to do with cryonics. Now, the correct experimental process for testing this to see if cryonics works is to select some subjects, select N subjects. I'm not sure why it's N, but it's always N. Select N subjects, cool them to the temperature of liquid nitrogen. Now we vitrify them down to that temperature. Wait 100 years, and then seeing if the medical technology of 2100 can indeed revive them. Now, we have a problem, which is that we do not have the results of that experiment today. The correct answer to does cryonics works is, well, from the point of view of clinical trials, come back in 100 years, the experiment is ongoing. And the question that we have to ask ourselves today is, do you want to be in the experimental group or the control group? We have a high degree of confidence about what happens to the control group. We do not have a high degree of confidence about what happens to the experimental group. And in fact, I think the odds for the experimental group are very good. And in fact, this leads to a payoff matrix. There are one of two possibilities. Either cryonics works or it does not. And either you sign up or you don't. If you do not sign up, or if cryonics does not work, then the outcome is the familiar one, and it's uninteresting. But if cryonics works and you sign up, then you will be welcomed into a future of very advanced technology. We know it's going to be very advanced because we have to have the advanced technology to revive people. And you'll be awakened into a future where basic value of human life has been preserved, because if basic value of human life is not a value, if that's been lost, you won't wake up. So we have pretty much of a guarantee that if you wake up, it will probably be a pretty good future. A critical point is that cryonics is not about freezing people who are dead. Death, a permanent cessation of all vital functions, is exactly what we expect not to happen, at least I expect not to happen, with cryonics. We expect a temporary suspension, followed by waking up and again being healthy. And if you meet someone on the street and you say, hello, how are you? And they say, I'm fine. And you say, but I thought you were dead. And their response likely is, well, no, the rumors of my demise have been greatly exaggerated. I am, in fact, alive, as you can see. Oh, I did spend some time while I was legally dead, and we know law and reality go their separate ways. I've been legally dead for a while, but I'm over that now. I'm all better. So what can I say? Basically, our position is we dispute the diagnosis of death. We want a second opinion from a future physician. This idea that it's hard to tell when someone is dead actually goes back to ancient times. Democritus, in around 400 BC, asserted that there are in reality no characteristics of death sufficiently certain for physicians to rely upon. And he was being quoted by Aulus Cornelius Celsus, who wrote De Medicina, which is a text dating back to about the 1st century AD. So we've had this concern about how do you tell when someone is dead for a long time. And in fact, there have been problems with the diagnosis of death. In the 19th century, people were alarmed by the prevalence of premature burial. And as a consequence, they often requested as part of the last offices that wounds or mutilations be made to assure that they would not awaken. Embalming received a considerable impetus from the fear of premature burial. You would often find, compared with today's statistics, you would often find that people were in fact buried alive because the diagnostic criteria were rather rough and were not always accurate. Today, if you look at modern definitions of death, and you go to the philosophers who are talking about it, and I'm quoting particularly from Robert Veitch, basically there continues to be this same uncertainty about what it is to be dead, and people bemoan the fact that our current medical criteria are inelegant and don't seem to have any theoretical underpinnings and are justified primarily by an empirical result, which is that people who are declared dead don't very often wake up in the morgue. And seriously, this is exactly what the definition of death is for. The definition of death is a pragmatic decision made by physicians today, and the decision is this patient has reached a point where none of the procedures with which we are familiar today is going to help. That's what death is all about. It's a pragmatic definition. It's a statement that our current capabilities, our current medical technologies are not able to revive the patient. There is no statement, there is no implied statement, there is no statement whatsoever about whether future technologies will or will not be able to revive the patient. And this raises the obvious and interesting question. Is there a criteria for death which is in fact solidly founded and which in fact would be applicable regardless of future advances in technology? And the answer is yes. It's been called information theoretic death. If the structures in the brain that encode memory and personality have been so disrupted that it is no longer possible in principle to restore them to an appropriate functional state, then the person is dead. In other words, if we can restore you in principle, if within the framework of the known laws of physics, it is in principle possible to restore you to a healthy, functional state, you're not dead. So with that thought in mind, we can now begin to look at our current environment. Our current environment, we have legal death on the one hand, which we require before we can be cryopreserved. And we have information theoretic death on the other hand, which we think in many cases of people who are cryopreserved, we believe they have not suffered information theoretic death. We have no reason to believe that that has taken place. So you can look at a lot of tissues that have been successfully cryopreserved, and there's a whole long list of tissues that in fact have been cooled down to low temperatures, have been warmed up successfully, which implies that the level of damage that takes place must be pretty small because tissues, a lot of tissues can survive the process. You find things like control studies on protein stability in postmortem rat cerebella show that the spectrum of abundant proteins is also unchanged after up to 16 hours at room temperature. So if someone says, gee, when you die your proteins fall apart, no, that's not true. There have been studies, the proteins are still there 16 hours later. That sounds like a good thing. You also find things like lysosomes did not rupture for approximately 4 hours and in fact did not release the fluorescent dye until after reaching the post-mortem or necrotic phase of injury. Well, I don't know what the necrotic phase is, but it sounds bad. But whatever it is, it's obviously taking place after 4 hours. And in fact, you find statements from a number of sources that say damage under the light microscope is not seen for from 12 to 24 hours post-mortem. And you also find that this claim that the brain dies after 5 or 6 minutes is incorrect. And to quote from Hassman, it turned out, in fact, that appropriate treatment of post-ischemic recirculation disturbances led to recovery of energy metabolism and neural excitability after complete cerebrocirculatory arrest of as long as 1 hour at normal body temperature. So there seems to be evidence for recovery of function after an hour under optimal conditions, and that's not the conditions one normally finds in cryonic suspensions. But it does indicate that things are preserved, structure and function are preserved longer than one would anticipate. You then start asking fundamental questions like, what is it we're trying to preserve? And the answer that comes back is, well, memory, structures that encode your personality, and we need to preserve those. A lot of that information is stored in synapses. It appears that synaptic changes are, as it's been called, the hallmark of long-term memory. And we see that synapses are preserved actually quite effectively by cryopreservation. We also find that once you've been cooled to the temperature of liquid nitrogen, you're going to be preserved for a long time very effectively. So the next question is information theoretic survival enough? And the answer is, in principle it is, and in practice I think it will be enough once we approach what is feasible in principle. Now, we will be able to engage in complete structural analysis and repair down to the levels of molecules and atoms. That's clearly possible in principle, and that possibility in principle is going to turn into a possibility in practice in the future. A major technology for doing this would be scanning probe microscopy or future descendants of scanning probe microscopes, which would basically be able to scan over a surface and analyze it. And not only would they be able to scan over the surface and analyze it, and gradually move through the tissue, removing structure, removing atoms, removing molecules, laying bare what lies underneath, and analyzing that in turn. For this to be practical with the volume of the human brain, you would literally have to have billions and billions of repair devices. If we had 3 times 10 to the 15th, that's about 1 million billion, so that's a lot. 3 times 3 million billions repair devices. So if you had that number of repair devices, they'd be able to go through the repair process in frozen tissue, tissue preserved at low temperature, in about 3 years. And that seemed like a reasonable set of assumptions on which to proceed. So if you want to, it was actually published in Medical Hypotheses. I discussed the various repair scenarios that would occur and conclude that there are a number that would work quite nicely. Cryonics is not for everyone. Not everyone, even if you provided 100% assurance, would decide that cryonics was a good idea. And to give you an example, Shirley MacLaine has said everyone who has died and told me about it has said it's terrific. So I think that she would decline the invitation, even given absolute assurances that technically it would work like a charm. So if I can close out with a quote from Bones McCoy, "Don't leave him in the hands of 20th century medicine." The most familiar example I can give for cost is the cost of computers. You've probably noticed over the years that computers keep getting less and less expensive, that Moore's law is doing remarkable things to the cost of computers, and it's continuing to do remarkable things. So when I talk about molecular repair devices, we're going to see a similar cost curve on those as well. They'll presumably start out very expensively, and as time goes by, the price is going to get lower and lower and lower and lower. There is, in principle, very little other than the raw cost of raw materials and the raw cost of energy to limit the kind of costs that you're involved with. And in fact, if you look at the raw cost of energy, the raw cost of energy is going to plummet at some point. Once we have low-cost ability to use solar energy, we'll be able to absorb sunlight, convert it into power, and if you price out cheap land in the outback of Australia, or even if you just take cheap land in the US, you find that putting up solar collectors results in power which is several orders of magnitude cheaper than what we now enjoy in electric power grids. So basically, costs are going to go down, and at some point the cost is going to be less than the sum of money in the Patient Care Trust Fund, which has been set aside to keep you in cryonic suspension, at which point you can be revived. Basically today, with the current vitrification protocol that Alcor is using, if you are suspended under good circumstances, and that happens to a fair number of cases, then I am forced to conclude that the odds of success are better than 90%. And I am forced to that conclusion by the fact that we are preserving all of the structures that we believe are important to long-term memory. And at some point, once you have a technology which is literally able to analyze the structure in molecular detail, you can repair everything else. So one of the big concerns is fracture damage. From a functional point of view, fractures are very bad. If you have tissue that is cooled and fractures and you warm it up, it's like someone has sliced it with a very sharp knife, which is a bad thing. But if you look at the information loss in that kind of damage, you find that if you cool it to liquid nitrogen temperature, you get a fraction. As long as you keep it cool, there's no information loss. These fractures, I should point out that freeze fracture techniques are used to actually examine surfaces in literally molecular detail. If you freeze fracture a sample and then analyze the surface, you can see individual protein molecules on that surface. So the expectation is that while present techniques are not yet at the point of being reversible, nonetheless they are providing excellent structural preservation, and the kinds of things that we think are involved in storing long-term memory and the synaptic structure of the human brain look like they are well preserved. Now, there's a bit of a debate here. Obviously, what we would like to do is say that we have preservation techniques that work by just cooling and warming and having the tissue function. And we would also like to say that we have a repair technology that can take pretty bad damage and repair it. And we'd like to make both these arguments simultaneously, because in order to persuade people that cryonics is actually a reasonable proposition, it looks like we need a lot of margin in our arguments, because people are hard to persuade on this subject for reasons that have been debated in the cryonics community for many years. But whatever the reason, there is resistance to the concept, and as a consequence, the arguments that we bring to bear have to be as strong as possible.